Okay, now that we've gone through all the conversions, we've done all the multiplications, divisions we can, now we need to get into how we round things off. Up to this point, you've been told how to round it off. Or you just typed it all out in the calculator and whatever it spits out you put down. And then you make sure the label is correct, or if you're not doing that, you need to start doing that. But that's not really the way it's going to work. And here's why. No number is exact. If it's been measured, no number is exact. Now, granted, the definition of a foot is 12 inches, exactly 12 inches. But if you have a ruler and you were to find 12 inches on there, you may not, well, you definitely will not have exactly 12 inches on there. It may be slightly off. It depends upon the machine. The machine, when it was calibrated, may have been calibrated incorrectly, and I guarantee it was. Every single one of them was incorrectly calibrated because it's impossible to get exactly 12 inches right on the button. You could be off by a trillionth of an inch and it won't be the correct answer or correct value. So your answer has to reflect what we call the weakest link theory, and that is that no chain is any stronger than its weakest link, and the same with measurements. No measurement is any better than its worst measured number. If you accurately measure parts of something and one of them is completely off, it screws the whole thing up. You have screwed up just by one measurement. Even if you measure 99 other things perfectly, as well as you could based upon the instrument you have, but you screwed up one of them, it's garbage. That whole collection is garbage. And so your answer has to reflect the precision of the instrument that you are dealing with. Now, that's different from accuracy. Accuracy, if you have a bad instrument, but you are accurate on the reading of it, that is the instrument's fault and not yours, okay? You are going to be as accurate as you can with the instrument you have, but it's the precision as to how good a measurement is going to be. All right, so let's take a look at some examples here. If I were to take a sheet of paper and I measured it with a ruler, on the centimeter side, the SI system side, I say, okay, here, that's 6.5 centimeters, okay? But if I take a close look again, it may not have been right on the 5 line, this 5th line after the 6th. It may have been slightly short or slightly past. Let's say it was slightly short and I found that it was actually going to be closer to 6.48. If it's not right on the line, you're going to have to estimate about what that is. But the meter sticks or the rulers only allow you to go 1 decimal place with the little lines for the centimeter, and then an extra decimal place if it's not exactly on there. That's purely estimated. That makes that 8 the doubtful digit. This 5 here was the doubtful digit, it's 6.5. Because that is never going to be exactly right. So, the doubtful digit determines how precise your instrument is. Okay? Now, if I get another tool and go 4 decimal places, oh, nirvana for scientists, 4 decimal places for measuring, stop it, it's so much fun. Anyway, let's say that I measure again with that particular instrument, and I get 6.4811 centimeters. Yes, 4 decimal places. That's not a perfect one, but it's certainly better than the 6.5, the 6.48. So now that 1 becomes the doubtful digit, not the first one, the second. It's been rounded off to that. Because we don't know what's going to be past that. Okay? So that's our best one. Let's suppose we make a rectangle with that line that I just measured on the paper. And I know that's a 6.4811. And then somebody else, I tell somebody else, go measure that, and they grab a meter stick, and they got 3.44, and they wrote that down. And then I find the area of that. Well, here's what it kind of looks like, except for my artistic ability is about that of a typical chimpanzee. But when you multiply these together, your calculator gives you this value right here. My question to you is that really the answer? Well, we don't know, do we? Because we got a really good measured number and we got a really stinky one right here. It's stinky. It's just stinky. So it has to reflect that number right there. So we have to go into something called significant figures. Significant figures are numbers that are actively involved in a number. That includes the doubtful digit and everything that is measured with that doubtful digit. In this case right here, the doubtful digit, the number that it's been rounded off to is this one right here. And that means all these numbers up here were actively involved in the measurement. That gives this 5 significant figures. This is the doubtful digit right here. I'm going to use DD for that, for doubtful digit. And everything in front of it is now the doubtful digit, or is now a significant figure. So this gives us 3 significant figures. By the way, if you want to be a hip scientist, you can say things like sig figs. You know what I'm saying? Sig figs. Anyway, so we can't have an answer that goes 6 decimal places because it doesn't really reflect how good those measurements are. So we have to examine the significant figures in order to do this. Okay, so let's take another number here. Let's now that I've done those numbers here, let's take a look at 965. Say 965 meters. And how many significant figures is this? Well, this is pretty easy to figure out because we know that that 5 there is the last number put down there, and that makes that a doubtful digit because we round this off to the nearest whole number. So that's your doubtful digit, and everything else in front of that is significant, and so this gives us 3 significant figures. But what if I put a 0 in that? Say 9,065 meters. Well, the doubtful digit is still that 5. And everything in front of it then becomes actively involved in the measurement, including that 0 that I threw in there. It's still significant, so that's 4 significant figures. But zeros start to become a gray area, and this is where the confusion can be. So you need to follow me on this logic here, okay? Let's suppose that the 0 was placed at the end. What's the doubtful digit here? Is it the 0? Well, unless we're told otherwise, no, it's not. Because we don't know if this has actually been rounded off from a number like 9,653.8147 meters or 9,649.523 meters. We don't know. We have to be told that. If we're not told that, then we have to assume that this has been rounded off to the nearest 10. Here and here. This 9 is greater than 5, that kicks it out there. This is 9,649.523. This is 9,653.8147. And so when we round it off, we have to leave the 0 there. Why? Well, if I drop the 0, that gives me 965 meters. That's not the same thing. We changed the number completely. The measured number has to be about the same when we round it off. So the 0 has to be put there. The fact that it's there means it's not actively involved in the measurement. It's there to keep the number from being different from what it was measured as. So the doubtful digit stays as this 5. And all the numbers in front of it are significant. This is 3 significant figures. we have a name for the zero. Mr. Poopy Pants. No, that's an immature name we gave it. We just have fun with those zeros. Wacky us. No, the name for this is placeholders. Zeros that are there after rounding off are simply keeping the number from changing from what it approximately was in the first place, and therefore are not actively involved in measurement, and therefore cannot count as a doubtful digit. Okay, so this is 3 significant figures because of that. Okay.